Please go ahead. I don't want to speak here.
Welcome, ladies and gentlemen. Thank you for this introduction. My name is Sebastian Henschel, and I will present you the talk effect of non-metallic inclusions and shrinkage cavities on the dynamic fracture toughness of the high-strength cast steel. So let's move on to the outline of the presentation. First, I want to give you a short motivation to this talk. Then I want to give you information on the materials and methods, so show you the investigated steel and the test setup. I will also give you the details of the results, photographic analysis, the strength and deformability behavior, and the dynamic fracture toughness tests. And of course, afterwards,
Hold the microphone closer.
okay. And we also performed the photographic analysis, and I will also sum up these points. So, as you might know, non-metallic inclusions can originate from wear of refractories or the melt treatment, and especially aluminum originates from the deoxidation treatment, and together with the dissolved oxygen it forms alumina in the steel melt. And in the solidified steel we have then the detrimental effect of the non-metallic inclusions in terms of deformability and toughness. So the aim of the present study was to form endogenous non-metallic inclusions intentionally and under well-defined conditions. We investigated the spatial distribution within the cast, and of course to characterize it with mechanical tests. So here's the steel. It's high strength, quenched and tempered steel, G42 bromo 4. After the heat treatment we have a tempered mod inside and quite high strength, which are given here. You see that there is a quite high sulfur content, so this is also pointed out here, and this leads also to some non-metallic inclusions. So for we produced the steel in a so-called steel casting simulator. Details are given in the paper here. This steel casting simulator contains an argon atmosphere and an induction heating system. The steel melt was handled in a crucible made of alumina and alumina magnesium spinel, and the handling was done with an oxidation and deoxidation treatment according to the scheme shown here. We have the temperature and the oxygen content measured over time. First we oxidize the steel melt with addition of iron oxide, and then we deoxidize it with pure aluminum. And what follows is cylindrical, after cooling there is a cylindrical steel specimen with the dimensions, and from this cylinder samples were cut for metallographic investigations, tensile tests and fracture toughness tests. And due to the cylindrical shape we also use cylindrical coordinates, which are given here. So let's have a look at the test setup. Of course we performed the quasi-static and dynamic tensile tests, and also dynamic fracture toughness tests in an instrumented sharp impact testing machine with we don't use the full energy, just a small energy of 15 joules. These are standard notched and pre-cracked specimens, which are also equipped with a strain gauge near the crack tip, which was statically calibrated to measure the force, and also a force measurement in the top of the sharp impact testing machine was applied. And this strain gauge was also applied to measure the critical point of the test, and at this point of instability the J integral was calculated. Afterwards, the fracture surface analysis was performed with the scanning electron microscope. So let's have a look at the results. First, the metallographic observations of the aluminum oxide inclusions. As you can see here, these inclusions have a median diameter of smaller than 5 microns and particle distance. This is the equivalent circle diameter of the inclusions, and relatively large particle distance of about 115 micrometers. Only inclusions some millimeters away from the crucible lining were measured. Directly to the crucible, the measurement was not performed because there was a very strong aggregation, which was then not found in the specimens for the mechanical testing, and so only the relevant inclusions were measured. So this were the aluminum oxide inclusions, and then we also measured the magnesium sulfide inclusions. These have a similar diameter, but the particle distance was much lower when we compare this to the aluminum oxide inclusions. This is due to the structure of most of the manganese sulfide inclusions. Here you can see an aluminum oxide, and the manganese sulfide is mostly in the dendritic structure, which were when the dendrite is of course cut in an arbitrary plane. And we can see also here that there is no angular dependency on the distribution of the non-metallic inclusions. So the tensile test showed the following results. Here we have the ultimate tensile strength and the yield strength over the radial position and at different height levels. We see only a slight dependency of the yield strength and the ultimate tensile strength of the radial position, and nearly no effect of the axial position on the yield strength. And when we have a look at the deformability, the elongation at fracture, and the reduction of area, we can see here that specimens from the top of the cylinder had a quite high elongation and deformability, but specimens from the center and from the lower part of the cylinder had a lower ductility, and which is also causes also a lower strain hardening, which is seen here by the lower ultimate tensile strength. When we have a look at the strain rate effect, we can see this is expectable that an increase in strain rate causes an increase in yield strength and ultimate tensile strength. There is no significant effect of the strain rate on the deformability, but as you can see, there's a slight increase of the deformability, and this is only attributed to the deformation heat, which is generated in the tensile test. There's there's no dependency of the radial position. So now let's have a look at the dynamic fracture toughness tests. You can see here that there is of course inertia in the first part of the experiment. When we compare the tap measurement, the forces measured by the impacting tap, and the force measured by the strain gauge near the crack tip, we can see these differences here. But after some time, inertia effects can be neglected, and we can see also some certain nonlinear behavior prior to the instability point. The instability point is here, and this is not very good, could not be seen very good here, but this point of instability is detected by the strain gauge near the crack tip. and prior to this instability there is some stable crack growth, and afterwards there is the unstable crack growth. And to characterize this point of instability, we use the J integral, and this is plotted here. And you can see here a quite large scatter of this toughness at the point of instability. And yeah, this large scatter is of course due to the non-metallic inclusions, but also due to the shrinkage cavities, which I want to show in the next slide. Here's a picture of the fracture surface of a tensile test. You can see here some aluminum oxides, which are mostly have a globular shape, and also some globular, very small magnesium manganese sulfide inclusions. And these inclusions, of course, initiate voids and cause the ductile fracture. In the fracture toughness test, we obtain such a fracture surface, and here also dendritic manganese sulfide inclusions were visible. And these these dendritic inclusions have a much more detrimental effect compared to the globular inclusions. Also, some small amounts of cleavage fracture surfaces were, or cleavage fracture facets were observed, but it's mostly the mechanism is mostly a ductile fracture. So to sum up, in the steel casting simulator, we generated endogenous alumina inclusions, but these alumina inclusions were mainly observed near the crucible wall. And due to the high manganese sulfide content in this batch of the steel, also manganese sulfide inclusions were formed. We had only slight effects of the location within the cylinder on the strength, so it's quite homogeneous. But we observed the highest deformability at the top of the cylinder, and because mostly at the bottom of the cylinder shrinkage cavities were observed. These were only relatively small shrinkage cavities. And as I told, the dendritic MNS or the manganese sulfide inclusions pronounced, of course, the damaging effect due to it acts mostly like a crack. So, and an outlook is we will focus on the aggregation of the alumina at the crucible wall to also study the effect of the crucible coating for this aggregation behavior. And of course, we should close all the shrinkage cavities by hot isostatic pressing to reduce the effect of the shrinkage cavities. Yeah. Thank you very much for your attention. Feel free to ask.